Hi, we are going to talk today about periodic trends. That's just a fancy way of saying that there are some qualities in the atoms on the periodic table that follow certain patterns. And we're going to look at three of them in particular: electronegativity, ionization energy, and atomic radius of atoms. So let's start with electronegativity. And I know you've heard this term before, and just as a reminder, electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. So what in the world does that mean? It just means that if elements were human, some of these elements would really want electrons, and others would kind of want to get rid of them. So the ones that really want electrons would have high electronegativity. And you can see on this scale that fluorine has the highest electronegativity out of all the atoms. And why is that? Well, if you remember from studying electron configurations, these elements right here, the noble gas elements, are very special. They have a full outer energy shell, with their valence electrons. So it's called an octet. They have 8 electrons in their outer energy level. And that makes them extremely stable. These elements are very, very stable, very, very happy. And for the most part, all the other elements would kind of like to have their electron configuration and have a full octet for their valence electrons as well. So fluorine right here is very close to having the electron configuration of neon. It could gain just 1 electron. It could look like neon. Otherwise, it would have to lose 7 electrons to look like helium. So fluorine has a very high electronegativity. It really desires to gain an electron. So going across the periodic table this direction here, you can see how lithium would certainly have a lower electronegativity than fluorine. It is not able to attract all of these electrons in order to look like neon. It would really rather lose an electron and look more like helium. So another important point to note is that electronegativity also decreases as we go down the table here, so that francium has the lowest electronegativity value out of all of the atoms. It is the least able to attract electrons to itself. And one more important point to note is that electronegativity values they're really a comparison between the different atoms. They're not, they don't have units. For example, there are several different scales that have been developed, and the common one has fluorine as having electronegativity value of 4.0 and francium of 0.7. Those are the assigned electronegativity values, and those are obtained by basically conducting a lot of experiments with each of the atoms and seeing how they bond with other atoms and taking a lot of notes of comparison. So that's how that scale works. Let's now look at ionization energy. Ionization energy is the energy required to remove an electron from an individual atom in the gas phase. So it's very much related to electronegativity. We see up here that helium has a very high ionization energy, and what that means is that it takes the most energy to remove one of its electrons than it does to remove an electron from anyone else on the periodic table, any of the other elements. So why is that? Well, for one thing, let's look at the trend going down. As we go from helium down to radon, we are increasing the energy shells, and the electrons are getting further and further from the nucleus. So there is less and less nuclear attraction and nuclear pull and force going on between the nucleus and those outer electrons. So that last electron in the very last shell of radon does not take nearly as much energy to remove as it does from helium, where the electrons are pulled in very tight and there is a great amount of nuclear attraction and nuclear force between the nucleus and that electron. So here, as we go from this direction over to this side of the periodic table, we have elements like lithium. Lithium only has one valence electron. It takes a lot less energy to remove that valence electron than it does to remove, say, one of fluorine's valence electrons. Fluorine has 7 valence electrons. It is really actually much more interested in gaining an electron. Remember, it has a very high electronegativity value. It would like to get another electron and look like neon rather than lose one. So it takes quite a bit of energy to pull one of fluorine's electrons from one of the fluorine atoms. Another thing to note is that these values, the ionization energies, are determined experimentally. People actually go into the lab and remove an electron from the atom, and then they measure how much energy it took to do that. So, for example, helium, they have discovered that it actually takes 1.31. Wow, that's a really fat marker. Let's do something a little different there. 1.31 megajoules per mole of energy to remove a helium atom. A megajoule is 10 to the 6th joules. So it takes quite a bit of energy to remove that electron. And just as a comparison, calcium over here is only 0.63 megajoules. So it's a little bit less. And that's just for an example so that you can, 0.63, so that you can have some idea of how much energy we're actually talking about. There are also experiments to determine the second ionization energy and the third ionization energy, where they remove a second atom or a third atom from that element. And those, of course, require a lot more energy than just the first ionization energy. Now we have atomic radii. The atomic radius is, of course, the length of an individual atom's radius. So it's not that surprising that this is highly related as well to the ionization energy. We have here down at this end of the periodic table the largest atoms, and up here we have the smallest. The trend usually goes like that. Just to give you some numbers, let's write a couple of numbers down here. Fluorine happens to be 71 picometers, and a picometer is 10 to the negative 12th meters. That just gives you a little idea on size. Let's look at potassium is 220 picometers. So that just gives you a little idea on size. Obviously, as you go top to bottom on the periodic table, you're going to get larger, simply because the energy orbitals are greater. You have electrons farther away from the nucleus, and the atoms just get bigger. So why the trend to get larger this direction, or perhaps smaller this direction? That is because as we go from left to right, the electrons are increasing in number within that energy level. And because of that, there is a greater nuclear attraction between the electrons and the nucleus. So the atom sort of pulls in tighter because of that attraction. And so it actually gets smaller going from left to right. And then once you increase in energy level and you go down to a greater energy level, of course, the size then gets bigger. So as a quick summary of the periodic trends, electronegativity, which is the ability of an atom in a molecule to attract shared electrons to itself, basically hog the electrons. Electronegativity increases going towards the right and going up, so that we have our highest electronegativity value in fluorine. Ionization energy, then, you'll remember, is the energy required to remove an electron from an individual atom in the gas phase, and that energy increases towards the right and going up as well. It requires a lot more energy to take an electron away from something that really wants to have it. Then we have the atomic radii. We have the radius increases as we go down, and the radius increases toward the left. So those are the summary of the periodic trends we're going to talk about today. One more item to note, and that is just ionic radii and the size of ions. A cation, if you'll remember, is the positively charged ion. One or more electrons have been removed to make that positive. An anion is the negatively charged ion. It has either one or more additional electrons that have been added to it, and it's just something to note that a cation is always smaller than its parent atom. Okay, so here we have the parent atom of lithium, and we have the cation. An electron has been removed from it, and therefore it is a smaller ion. For an anion, it's the opposite. An anion is always larger than the atom from which it was formed. So here we have the fluorine atom and the fluorine ion. An electron was added to it, and it has increased in size as a result. So thanks, and we'll see you in class.